at 3 dm distance, ILS glide slope shows two dots fly up indications on a 4-dot indicator. Approximately how many feet aircraft is above or below glide slope? Now, this 4-dot indicator, the CDI display, okay, gives us the solution. It gives us a solution to a problem, right? So if it tells us to fly up, that means the problem is we are flying down. We are flying below the glide slope. We are flying below the glide slope. We are required to stay on the glide slope, but we have deviated below the glide slope, and therefore the CDI indication tells us to fly above the glide slope. And how many dots? Two dots above the glide slope. So let's say this is your runway. This is the standard 3-degree glide slope. Your aircraft is below the glide slope somewhere here. Okay, somewhere here. And therefore, the CDI indication tells you to fly two dots up. Two dots fly up indication. So we have to find out how many feet you are below the glide slope. So that means this distance you have to find out. Okay. So now on a four dot indicator, one dot will be equal to 0.175 degree. On a four dot indicator, glide slope, one dot will be equal to 0.175 degrees. One dot equals to 0.175 degree. So two dots will be equal to 2 into 0.175, that is equal to 0.35 degree. So your aircraft is 0.35 degrees, okay, 0.35 degrees below the 3-degree glide slope. Below the 3-degree glide slope. That means with respect to the ground surface, we have this triangle. We have this new triangle. Okay, and the angle of this triangle, this entire triangle is 3 degree. 3 degree minus 0.35 degree will be equal to 2.65 degrees. 2.65 degrees. What is the horizontal distance? We are 3 nautical miles from the runway. We are 3 nautical miles from the runway. Okay, so 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 let's find out this vertical distance. Let's use this triangle and find out the vertical distance using tan theta. So tan theta is opposite side upon adjacent side. So tan of 2.65 degrees is opposite side is x. We have to find out that divided by 3 nautical miles. So x will be tan 2.65 into 3, that is 0.1388 nautical mile, multiplied by 6,000 feet. So that is equal to 833 feet. So this height is 833 feet. Now we will again apply this Pythagoras formula to the bigger triangle. To what triangle we will apply this formula? To this 3-degree angle triangle, this bigger one. Okay, whose angle is 3 degree, the standard glide slope. And then we will find the height above the ground. Find the height of this glide slope above the ground. So tan theta will be equal to opposite upon adjacent. So tan 3 opposite. Now we will find out this bigger x value. So I'm writing it in x. Okay. So x divided by adjacent, which is 3 nautical mile. So x will be tan 3 into 3, 0.157 nautical mile multiplied by 6,000 feet, 943 feet. Okay. So you have this bigger triangle side equal to 943 feet or approximately 940 feet. And we have this small side of the triangle equal to 833 or 830 feet. So this difference between them will be equal to difference between this 3-degree glide path and 2.65-degree glide path where your aircraft is currently situated will be equal to 930 or 943 minus 833, which is equal to 110 feet. 110 feet. So that means aircraft is approximately 100 feet below the standard glide path. Okay. So how many feet aircraft is above or below? Aircraft is 100 feet below the glide path. Next, on a map whose scale is 1, okay, so scale is equal to chart distance upon earth distance. So scale is 1 divided by 10 raised to 6. Earth distance is 400 kilometer. We want to find out chart distance in terms of inches. Okay, so therefore chart distance will be equal to scale multiplied by earth distance. So let's convert earth distance, which is 400 kilometer, into corresponding inch. So 1 kilometer is 1000 meters. So 400 will be equal to 400 into 1000 meter. 1 meter equals to 100 centimeters. So 10 raised to 2. Now 1 inch equals to 2.54 centimeter. So this much centimeter will be equal to how many inch? So 400 into 1000 into 100 centimeter will be equal to how many inches? Cross multiply. So that will be 400 into 1000 into 100 divided by 2.54. So final answer will be 400 into 1000 into 100 divided by 2.54. So that gives you earth distance equals to 15748,031 inch. Okay. Now we are going to use that here. So scale will be equal to 1 divided by 10 raised to 6 into 15748,031. So chart distance will be equal to divided by 1, 2, 3, 4, 5, 6. 15.74 inch. 15.74 inch. Simple. Next. After flying 1 hour 30 minutes at a speed of 150 knots, aircraft is 15 nautical mile off track. If the remaining time to go to destination is 45 minutes at a speed of 180 knots, what is the closing angle? So we are going to use track error and closing angle. Let's say this is your departure, this is your destination. So after flying for 1 hour 30 minutes at a speed of 150 knots, you will cover a distance of 150 knots into 1.5, 225 nautical miles. So that means after covering a horizontal distance of 225 nautical miles, you are off track by a distance of 15 nautical miles. Okay, you are currently here. So what is the track error? Track error angle. Track error angle equals to distance of track into 60 divided by distance gone. So distance of track 15 nautical mile into 60 divided by distance gone 225. So 15 into 60 divided by 225 is 4 degree. Next, closing angle. So join this triangle. Closing angle, that means you want to go directly to your destination. Okay. So this is your track error angle. This will also be equal to track error angle of 4 degree, and this will be your closing angle. So closing angle is this. So alternate angles are equal. So this closing angle will be equal to this closing angle. Corresponding angles are equal. So track error 4 degree here will be equal to the same track error 4 degree here. So now we will apply this formula to this side of the triangle. Closing angle equals to distance of track divided by distance remaining into 60. So what is the remaining distance? If the remaining time to go to destination is 45 minutes at a speed of 180 knots, so distance will be 180 into 45 divided by 60. That is 135 nautical miles. Substitute the values. 15 divided by 135 into 60 is equal to 6.6 degrees, approximately 6 degrees. So closing angle is 6 degrees. So find closing angle. So closing angle is 6 degree. This is your final answer. Okay. So closing angle is 6 degree. Your aircraft will have to turn a total 10 degrees to the right hand side to go to its destination directly. Next. As per ICAO yardstick, DME accuracy is plus minus 0.25 nautical miles plus 1.25% of the distance measured. So let's say you are 100 nautical miles from a DME station. Okay, 100 nautical miles from your DME, distance measuring equipment ground station. So your distance measuring equipment must show this value accurately, but there is some provision made for some error. So it can show a little bit more than 100 nautical mile, a little bit less than 100 miles. That is acceptable. So we have to find that range, the acceptable range within which your DME indication can be valid. So the formula is plus minus 0.25 nautical mile plus 1.25 percentage of the distance measured. So if the distance is 100 miles, so it will be plus minus 0.25 plus 1.25 percentage of 100. That is equal to plus minus 0.25 plus 1.25. So it can be 1.5 or it can be 1. If you add 0.25 plus 1.25, you get 1.5. If you subtract 0.25 from 1.25, you get the value of 1. So your DME can vary between 99 and 101.5. This is the acceptable range. 99 से लेके 101.5. If the total number of persons is not known at the time of boarding or filing a flight plan correction, what should you write in item number 19 in the flight plan form? So this is your flight plan form. Over here you can see item number 19, endurance persons on board. So there are three spaces. There is a block, there is a box, and there is in this box there is a space given for writing three alphabetic letters. And if you do not know, if you are unaware of the total number of persons at the time of filing this flight plan, you can write to be notified, Tango, Bravo, November. Just three alphabets to be notified in that flight plan form. So whenever ATC contacts you initially, uh, and you can notify the ATC controller about the exact number. Once you board your aircraft and once you have figures at your disposal, you can notify that number to the ATC. Frequency range of DME. So DME works in the frequency band of ultra high frequency starting from 962 megahertz up to a frequency of 1213 megahertz. Next, aircraft is on a VOR radial 235 heading 003 magnetic OBS 060. What are the correct indications? There is a VOR station radial 235 heading 003 magnetic. So in the north direction. What is the reciprocal of 235? So 235 minus 180 is 055. Okay. OBS. OBS is 060. Okay. Now you are to the west, to the southwest of this VOR station, and the radial that or the OBS setting that you have entered is to the northeast of this VOR station. That means if you want to go to this 060 radial, which you have entered in your OBS, you will have to go towards the VOR station first and then transition onto this radial, right? So the indication given to you, the indication that will be shown to you by this OBS will be 0602 indication, and what will be the CDI? Now the reciprocal of 060 is 240, and you are currently positioned on radial 235. 240 going inbound, 240 will be to the left hand side of 235. So you are flying inbound towards this VOR. Radial 240 will be to the left and you are to the right of it. Correct. So if you want to transition onto radial 060, your OBS indication will ask you, it will ask you to fly left, to fly left hand side. It will ask you to fly left hand side by some amount. So it will ask you to go to the left hand side, intercept this radial 240, then fly this radial 240 inbound, overfly this VOR station, and then directly transition onto radial 060. And when you overfly this VOR station, this will become from, and automatically the CDI indication will come in the center. Once you intercept this radial 240, the CDI needle will remain in the or come back in the center position. Okay. So now the difference between 235 and 240 is 2-degree difference. Correction, it is 5 degree 5-degree difference. Now on a VOR, questions involving VOR, one dot will be equal to 2 degrees. So 5 degrees angular difference will be equal to how many dots? It will be equal to 2.5 dots. 2.5 dots. So the needle will move 2.5 dots to the left hand side. Okay. So that will be your selection, or that will be the representation. It will show two indication. Okay, so option A is eliminated. Two indication will be shown and CDI indication will ask you to go left. So option Bravo is the right answer. Next. The use of high frequency in super high frequency band in airborne weather radar is essential to detect. It is essential to detect large water droplets. Now, large water droplets are associated with cumulonimbus or CB clouds, right? So we are concerned about large droplets, not the small droplets. So let's say this is a cloud and there are these large water droplets in this cloud, like this. And then there are some small droplets also, like this. Now, when you use your airborne weather radar in super high frequency band, the corresponding wavelength that you get is approximately 2.5 centimeter something. Okay, so when you use such a wavelength, this wavelength will penetrate the cloud layer, strike the large water droplet, and get reflected at the airborne weather radar. So that is how you get proper reflections from large water droplets. Because whether you get reflections or not depends on the size of the water droplets and the size of the signal. The large water droplets are also in around in the centimeter band. So that's why the wavelength, which is centimetric, is able to strike the large water droplet, which is identical in terms of size, and gets reflected from there. Now, small water droplets, which are not identical with this 2.5 centimeter wavelength band, so in that case, this signal will penetrate this cloud layer and go past this cloud layer. So you won't get any reflections from small water droplets because they are smaller than this measurement. Okay, so in order to get reflections, the wavelength measurement must be equal to the measurement or size of the water droplet. And that's why we use super high frequency band, because the corresponding wavelengths that we get with them or that come along with them is proportionate or is favorable to obtain adequate reflections from large water droplets. Next, how much is the vertical coverage of ILS glide slope? So, this is the vertical coverage of ILS glide slope. The standard glide slope will be 3 degree. 3 degree. Theta will be 3 degree. This theta you can see here. Okay, that is 3 degree from the ground surface. Now, the lower limit of that standard glide slope will be 0.45 times theta. So 0.45 multiplied by 3, and the upper limit will be 1.75 times theta. So 1.75 times 3. Okay. So this 0 is nothing but theta up to 1.75 degree theta up, and 0.45 degree theta, and down to 0.4 degree 45 degree theta horizontal, yes, up to 3.5 degree and down to 1.75 degree wrong, up to 3 degree and 0.45 degree. So correct answer is option alpha. 99 is option alpha. 1.75 degree times theta is the upper limit, 0.45 theta is the lower limit. Now, if the question gives you some ILS glide slope value like 3.5 degree, 3 degree, 2.5 degree, in that case you will have to do this multiplication. 1.75 times 3, 1.75 times 3.5, 1.75 times 2.5, whatever value given in the question, and then accordingly mark the option. Okay. Here in this question, no value was given. So we just wrote this formula 0.45 theta, 1.75 theta. All clock times in your flight plan are to be entered in four figures UTC. Four figures UTC 1505, whatever. Need not write this Zulu, need not write this day, hour, and minutes. Nothing like that. Just the four figures, hours and minutes. Simple. So this concludes our lecture. I hope you have understood all the 10 questions that I have answered in this video lecture. If you have any doubts, questions, feedback, let me know.